Hi there, and welcome back to this series tutorial. Now let's work in next tutorial, tutorial 3, and this one basically what we're going to work in this case. Okay, see that we have the classical convection diffusion equation. So in this case we are going to take away the temporal derivative diffusion term, and we have just convection plus a source term. We are going to work it out with this 1D geometry. We have here boundary conditions, and for this setup, this problem have an analytical solution. So I love this kind of problem where we have analytical solutions or manufactured solutions, because you can do a lot of things. So let's play a little bit with this case. We can put it into practice all the knowledge that we acquired in the two previous tutorials, but specifically here we're going to work steady simulations and the under-relaxation factors, and also the influence of the tolerances in the solution. Okay, so when we run this case, at the outlet we are going to measure the solution, and should be 1. Now look at here the influence of the under-relaxation factors on the solution. So see, as we increase the under-relaxation factors, we get faster convergence rate. So see that in 0.9, just for about 10 iterations, we get a converged solution, and we get something close to the actual value. But see that as we decrease it, as we decrease under relaxation, we use more iterations. But mysteriously also, that as you decrease this one, we are getting far from the actual solution. And the problem here is that it's not only the under relaxations, you have to take a look also at the tolerances. So now if let's say we fix the under relaxation at a given value, let's say for instance, so here we have it fixed at 0.1. So now let's fix the under relaxation and change the tolerance. So see that we're fixing the under relaxation in this case to 0.01. That will be equivalent to this case, and see that as we increase, now you have the fix on the relaxation, but see that you decrease the tolerance. And see that as we decrease the tolerance, see here, we get closer to the solution. But now we're going to see an increase in the number of iterations. So you have this under relaxation, but sometimes you need to be careful and use right tolerances. So under relaxation is a way to control steady simulations. Okay, but we have seen also that you can use it in unsteady simulation. So let's play with this case, and okay, also a little bit as you go to the theory, what is going on with the under relaxation is that these values, those values are bounded between 0 and 1. You can also over relax, but it's not recommended, usually will diverge. So the closer that you are to 1, the faster will be the convergence, but that not necessarily, as we saw in the example and the figure, that not necessarily will give you good accuracy. Okay, but you go faster, you lose stability. As you go closer to 1, you go slower, you gain stability, but again, not necessarily will give you accuracy. So also you need to be careful with the tolerances. And here you have, depending on the method that you use, this is the recommended values, the industry standard. But again, these values depends on the problem you're solving. This is not universal. It's not that always every case you can use these problems and you will get the best compromise. Okay, it's very problem dependent, but in most cases it's okay to start from here and then you can reduce or increase it. So let's work in this case. So as you go to your tutorial, you have here source scalar transport. Let's go here. So here we have 3 different directors. You see that the same problem we have using the solver: scalar transport form, simple form, and pimple form. Okay, here we go on steady, but we can play with the under relaxation factors. So I want to show you here that pretty much the same problem can be solved with these 2 solvers. So let's start with the scalar transport form. Okay, so launch your terminal there. So let me show you the case setup. The only difference here, or the new introductions here, is the auction. Okay, so as you go here we're introducing this implicit sorter. Okay, so it is 1. Okay, so here we have linear, nonlinear pair. We're adding 1 here, and volume specific is just you have to wait to add the sorter. You can add it in a volumetric way. Now this is the absolute, so it's the quantity divided the volume, or you can just add directly the values. So in this case, we use the specific volume mode. Okay, that's all. Then the boundary conditions is as shown in the figure. Okay, this is setup. Okay, so here we fix the value of the transported quantity to 0. Here we put our Newman boundary conditions, and the domain is 0, 1. So in this case, we're using a perfect mesh. We know how to deal with the correction, but feel free to use, in the previous case, we have the same dimensions with triangles and polyhedra. Feel free also to rerun this case using those meshes, so you will know how to adjust everything. So in this case, we take it, this is 1. So this is 1, this is mesh. So let's open the dictionaries in which we're interested. Okay, so as we go to SV skin, okay, look at that aesthetics case. Default goes linear for gradients. Then we have this skin goes linear. Okay, so this is the convective term. A scalar, remember, scalar transport is just one equation. We don't have velocity, pressure, or all the stuff. But in this case, we're going to do it. Limited 1. Okay, the 1 is recommended. And SV solution, we have our standard setup. And see that first we start with under-relaxation 0, 1, and then we're going and see, and here we're fixing the tolerance of the solver. So the solver will stop when reaching this tolerance between iterations. In this case, 1 non-orthogonal corrector. Remember, I told you, even if the mesh is perfect, I always recommend to do at least 1 correction. Okay, so that is to improve gradients. And here you can change the formulation of the simple. You have simple and simple C. By any means, I recommend you to use the consistent yes here. Okay, put yes, that is more robust, and it will let you use larger under-relaxation factors. In this case, it won't be much a difference. I will use consistent. Then you can also I will disable consistent, but if you want, you can run consistent and you won't see much different. But when you go into fully navigate result, there you see the difference. Okay, so let's run the first case. Okay, as usual, you have the scripts. If you want to see what is going on, just open the script and you will see everything. So as you see, very fast. Look at that, in 51 iterations we converge, and let's see also the convergence here. So see the iterative convergence. So see here, you start here, and then you have the non-orthogonal iteration. Okay, so as you increase this one, you will do more iterations, and you will improve your the accuracy. But see what I mentioned, that is a good idea to have between your initial solution and the first iteration as the non-orthogonal correctors, to have at least an order of magnitude reduction here. But here we don't have it. But in this case, it's not due to the fact that we need to increase this one. Actually, if we increase those corrections, we won't have much different in the solution. Okay, so see here that the solution, the outlet should be 1, and see that we have this one. So see that we have an unconverged solution. So let me show you that if I increase that non-orthogonal, see that I didn't improve much. Okay, so we have an improvement, but see that it goes from this to this. So it's not reducing the residual in a monotonic way. So the problem here is not this one, it's something else, and we're going to see that the problem, it is this here, the under-relaxation. So let's visualize, let me rerun, and let's visualize this solution. Okay, I will press delete, and I will just let you know also, when you open a folder and you see here a directory called Paraview, usually here you will have this state. This state means that you have here a paraphone state that will replicate how I want to visualize it. So to use that state, you go here, load state, go into PolyView, open the state file, and then here you have to be careful that you need to choose, okay, save files under a specified directory. Choose the current directory. Okay, so this is my current directory. Okay, sorry, it's this one. Okay, and it will replicate the visualization. Okay, so see that here we have the number of iterations. You press play, you see the evolution. So see that it stopped, and after 51 iterations, okay, it reached this convergence tolerance here, but it's clear that we can see here that we haven't converged. Okay, so how we can improve that convergence? Well, let's play a little bit with under-relaxation. So if I go 0.3 now, see that now 26, much better convergence, but still we have an accuracy problem. Okay, so if we press again PolyView, I don't want to load that one, I want to load this state. And I want to use this directory. If I press play, see that just 27 iterations, it reached a much better value. Okay, it's getting there, but still we're not there. Okay, so let me increase now on the relaxation, and if I go 0.5, see that now in 18 iterations, 0.9, so it's getting there. And what is going on here, remember with this tolerance, that it will stop when you reach the tolerance, the initial tolerance between this and this. It's less than this value, the residual, it will stop. So if you do your math there, you will see that you're fulfilling that condition. Okay, so let's move. Okay, so I want visualize, so I will go to 0.7. And let's see what happened here. That now we get closer, but still there is a small difference. So if I go to 0.9, okay, still there's that difference, but it might be something more numerical, some error, or related to the mesh. Actually, it is that. I will show you now. So delete low state. So in this case, I won't do it because already it's reading the right file. So see that it's running. I see that we have that different here that it's not very nice. Okay, but still we have some error. So let me go to 1. So 1 is the largest values that you can use, and usually if you're working steady, it will be unstable. So I don't recommend you to use 1. Okay. So in this case, it's working. See that it's using 11 iteration, but still we have a problem in the outlet. Okay, so remember that now to take into account for that, what we can do, or reduce the tolerance, or maybe let's see what is the influence of this consistent. I think it won't be much. Okay, as I told you, it's not much, but you will see the difference of using the consistent or no when you work with the navigator. So even if you increase this one, also won't be much different there. Well, probably will be some improvement. Okay, see that we have an improvement there. So if we go to 0.7, let's go 0.7 here. And see that we have an improvement. So by increasing the correctors, we have an improvement, probably that is a little bit large. So let's put 3 and see what we have here. No, so that's good. So we put 5. This is a good improvement. As you leave it to 1, or let's put to 0, as we have a perfect mesh, see that we have a large variation. So just to show you the mesh, this is a mesh, okay? It's a 1D case, it's an interior perfect mesh. So just to show you also, and as I mentioned, the beauty of having these cases where you have analytical solutions or you manufacture your solutions, is that we can increase the number of cells here. So let me go and put here 200. Okay, so see that a larger mesh, but we are not getting an improvement in the solution. So let's see what is going on here. So see that, as you recall previously, there were some fluctuations here. So see how smooth is this profile here. But what the problem that we have here is that we are far from the final solution. Okay, so what we need to do is that we improve the quality by increasing the the mesh number. Okay, let me add 1. And let's see if we have a difference in the solution. So remember this number and the number of iteration, 117, 0.41. Okay, so see that now we have 59 iterations, 0.4, a little bit better, but it's still there. But see that these are things that you need to always wait. That probably you will do more corrections. Okay, so per iteration your cost, it might be higher, but your overall cost will be smaller than using 0. So as I mentioned, that this is why I always like to do at least one non-orthogonal, because there is not a high cost of this iteration. As you put 2 or 3, you start to see the cost, but at least 1, even in perfect mesh, is not bad. Okay, but it's still we're far from the solution. Okay, so what we need to do now to improve that solution is that we need to improve this residual control. Okay, we need to get the converged solutions. So if I reduce this one by 1 order of magnitude, more iterations as expected, better solution. Okay, see here, but we're still not there because it should be 1. Now if I put there this, so that we're getting there. Obviously it's taking more iterations, so let's plus the solution. Low state, I have it here in PataView. Okay, so if I play, see that it's very smooth. As you run this quasar mesh, you will see that there are some jumps there. Okay, and see that you have this small difference there. Remember that also we need to play with the numerical schemes. Now we're just playing with the iterations here as the solution. So let me put it here, that should be okay. And 0.7 is okay. And here we were doing Gauss linear. So let's go, for instance, here. Let me go and put here linear win, this method. And let's run. 0.996. Okay, so if we plot the solution, dot state, we have here, so it's still some small difference there, so it means that you still need to iterate more to get there. So if I go and reduce my tolerance, or probably increase this one to 0.9, see that now our solution is where it should be. So you have some numerical garbage there, but it's 1, okay. And let's play now with the numerical scheme. So now we're using the linear win, the one that I recommend you most of the time, but let me go and change to Van Leer. So let me use now Van Leer there. Let me run. And see that Van Leer, first things is strange that you will see that you are taking all 1,000, the maximum number of iterations that I have in control to converge. So it's already telling you that maybe there is something that is not going very well there. So as you go back here and monitor, so look at the importance of monitoring always your minimum and maximum values. That, as I mentioned earlier, for me is a standard. So see that maybe your solution is becoming a little bit unbounded. So that might be the problem in the Van Leer. So if we visualize, So sometimes these methods sometimes requires that you use a small variation of the solution. So that means small CFL number at the beginning or a small under-relaxation factors at the beginning, and then you can increase that under-relaxation slowly. So if I press play, so let me go to 0 and see what's happening here. So you see that you have many oscillations, and then it will start to stabilize. But see that the Van Leer actually at the beginning it is unstable, but then it will stabilize. But that is not a good behavior, okay? Because that at the beginning, in this case, we have a physics that is not very complex, but in a complicated physics, this will immediately diverge, or it will keep converging, but it will converge to a very large value, a non-physical value. So probably, let me go back to the mesh here that we have 20. Okay, so that is the stabilizing factor in this case. And here, let me put this one 0.1 and put this one 0.7. So if I run this case, okay, see that in 17 iterations it's stopping, but see that now at the outlet, when I measure that quantity, that should be 1. I have here an error that is about 10%. This is a large error, and this is not acceptable, okay? But here you can see that there is a fluctuation. See that in one point is going to 2, that in reality that shouldn't happen because that we have that soul stir there. So if we play that solution, we're going to see all kind of iterations that are happening, of oscillations happening. So press here. And see that you have at the beginning, see that how crazy they feel at the beginning. Okay, so see that you have all these oscillations propagating, then it's slowly stabilized, okay? But this is not a good behavior, okay? Just to stress here that not always a TVD is a good choice, or put it at the beginning when you have, let's say that the solution is starting and the physics still is not settle. It's not a good idea. So it's always better to start with something like linear win, or probably you can start at win and then the solution keeps evolving, just go to the large accuracy. But now let me go to the min-mod, and you will see that min-mod is a little bit more dissipative than the Van Leer, but in this case it will give much better results. So you see that 8 iterations converge very close, and see that we don't have those oscillations there. So this is another example just to support when I tell you that I really like the min-mod. It has very good properties, very stable. Okay, it's less accurate like any other TVD, but it's much better than the linear win. But again, it's not always you need to use it. The linear win is okay. We run this one and you saw that the linear win gave good results. Okay, so you see that we have a very good agreement with the analytical solution, the red one. So at this point, to get much better agreement, so then you can play with the others methods. So as you go to Super B, probably I think this one will diverge. You see it's diverging, and the point is that we are using a very large URF. Probably I think if we reduce this also, it will diverge. You see it runs more, but it will diverge. So this is a case, even that it might seem that easy physics, the Super B will have problem because it's too compressive, okay? And you go with these others and we'll have the same problem. But let me focus with the min-mod. We have that. Let me reduce accuracy here just to get more accuracy, the tolerance to get more accuracy. And if I run, see that I close to 1. So see the influences, you go here, 0.1, you see that, again, you are there. So remember previously, we were putting here 0.01, running, and see that we're far from the solution. So you can still use this small URF, but then you need to improve your accuracy here. So see that you are getting closer, and you reduce it, you get closer. And also monitor, see that our solution is stable, it's not oscillating. Okay, it's increasing in a monotonic way. See that again, here we're good agreement, 100 11 iterations. So probably here there are some oscillation, but this is less than 1%, but it's probably something that you can control. Let's see, we'll actually see that here we have some oscillations. Okay, but probably here is more related to the mesh. So as you increase this one to, let's say 200, we might get a better agreement. So this is 700 iterations, okay? And see that it is still increasing, haven't converged yet, but now I can control that by increasing my under-relaxation. So usually 0.7 is a good value, but again, this depends of the problem. But see here that by increasing that, okay, we greatly accelerate the convergence. It's still a little bit far, okay, but we know what is going on, what is happening. Okay, so let me put there this one. Okay, and if I go 0.9, see that now it's getting to 1, but it has those oscillations. And as you go to 1, we are going to exacerbate those oscillations. See that here we're about 10%. And remember that it's always possible to, instead of under-relax, over-relax. It's not recommended, and actually it's not a good standard practice. And seeing that in this case, it is converging, it is iterating, but it's converging to a wrong solution. This is what I mentioned, that it's always important to monitor minimum and maximum values, because you don't monitor this one, you will say, okay, my solution is converging, you are wasting 1,000 iterations, because if you were monitoring that, you will realize at the beginning that, okay, look at that, there is something wrong there. Okay, so to put minimum as a maximum is here. Okay, you enable or disable that. So if you are running without this one, you will go like this. See that you don't have any information what is going on. For you, that will be, okay, it's converging. Maybe you will look at the initial residuals, you will realize that they're a little bit high. But sometimes even these residuals can be low. And you just realize at the end that your solution is completely wrong. So my advice, again, is always monitor those minimums and maximum values. So let me load the state here. And see here that it is just at the very beginning is already divergent. So iteration 1 already you have not that divergent, but that convergence to the wrong solution. One quantity is becoming very, very unbounded. So let me go back here to enable. And again, you have many more methods. You can play with all of them. Okay, you have many methods implemented, but you will realize, as I mentioned, you stick with a win, linear, and a good TBD. That's all. We have also additional here, the limited linear. So let me put it here. I have this one. So let's see, and let me go back to the mesh 20. This is okay. 0.9. And let's see what we have with this method. It might be, so this method is getting good accuracy, but it's going to 1,000 iterations. Let's see what is going on. So the limited linear that we are using here is a bounded variant of the linear method. So in the case that you have some strong gradients, it will, if I would recall, it will default to a wind. Okay, let's say, so it's a pure linear plus the upwind for strong gradients. Okay, iteration 1, see that it's oscillatory at one point and then it's stabilizing, okay? So yeah, it's doing a good job, okay? Probably it's not ideal. So play with all these methods, okay? So let me go 0.1, run. So this one should stop at 7, okay? But my choice will be this. So this is the setup that most of the time you will use. So steady state, we have seen also that gradients have an influence. So in this case, if you want also, just to stress that my setup probably will be this one. You enable the gradient limiters, then use the linear win, and then limit 1. When it comes to SV solution for the steady, at least do the one on orthogonal always depending on the quality of the mesh. The consistent formulation probably is the best one. Okay, probably not is the best one. And be careful with residual controls. And also on the relaxation, that they are very problem dependent. So here you have the industry standard. So if you're using the simple formulation, in the full Navier-Stokes, you would put pressure 0.3 and then 0.007 for the rest, and the simple C, something like this. But not necessarily this will be always the case. Sometimes with compressible flows, you will add density H or internal energy, so you will need to relax those also as well. So here we're applying on the relaxation to T, okay, is the scalar transport, the variable that we're transported. So we have the gradient limiter, the new thing that we added, and see that actually by adding the gradient limiter we have a much better behavior. In 4 iterations it's convergent, and we don't have any more those strange oscillations. And let me reduce here to 0.3. Okay, so now is the problems will be with the tolerance here. So if you increase this one, you might get to the value. So here is you put 0.1. So here we're going to the starting case. So this is our starting case. See that stop in there, then you reduce your tolerance, and you will get closer to your value. Okay, so see that actually here we're already in the value. So this is a compromise. You see that you reduce something, but you're increasing the iteration. So you need to do there, let's say, analyze what you are doing. Sometimes it might be a good idea to reduce the tolerance. Sometimes it might not be a very good idea because you are not getting much in improvement in your solution. And also take away on the relaxation factors are very problem dependent. So this was the solver scalar transport phone. Let's move now to simple phone, okay? The actual solver that we might actually use for industrial problems. So let me go here to the default settings. Default 2020. Okay, so we move here to simple phone. Okay, so the setup is exactly the same. We're adding that source there, so this is we're using actually here. Well, you have some animation what's going on, and if we open SV solution, SV skin, these are where we're going to work. And then in Control D, we're adding that source here. So see that we're adding the scalar. Okay, it's being transported, diffusion 0. Okay, so we don't have no diffusion coefficient, 1 correction. Here's where you control the correction for the scalar transport, and here we add the source there. Okay, then SV skin, and also remember to go constant. Here you will have transport property new 0, so we're not solving for viscosity. And see here that we have the setup that I mentioned. Okay, set limited Gauss linear. Okay, so here you declare this variable and then you can use it here. Okay, see here that we're using for divergence of u this method, then divergence of t this method. Okay, so pretty much this setup is equivalent to the one I showed you previous with the scalar transport. This corresponds to the turbulent variables. Okay, we don't have turbulence, but you need always to declare this one, so it's some term that arise in your discretization. And limited one, and this is related also to turbulence model. Even if we don't have, you should put it there. And here, well, you have all your tolerances solvers, and it's simple. We're using consistent residual control for T. Okay, so the variable that we're transporting here, we can set up the residual control here, 1 non-orthogonal, and here you have your relaxation factors, and then here you show you different ways to set up. So see that you put this notation, regex notation, is you are applying this value to all variables, but also you can do it in a selective way. So you can go by pressure, by U, by variable. Okay. So let's run this case. In 46 iterations, it's running. So now here we're solving the full Navier-Stokes. So you see that we have U, P, we have the pressure velocity coupling, but the solution is pretty much the same as the previous. So this setup, see that is giving, this setup is giving 0.5, previously it was 0.51. So see that are very similar. Okay, and the idea would be exactly the same as previously. Okay, so you can reduce your under-relaxation factors, or you can increase, you can reduce your tolerances, so you play around with that. So if I go here and let me reduce by an order of magnitude, it's taking more time, but see that it's getting closer to the value that we know is 1. So if I go here, let me reduce this one, will take much longer, but it might arrive. So actually it arrived to the solution, and it didn't took that much longer. Previously it was 87, something like that. Look at that, 10 more iterations. It's not bad. So let me run Python. Load state. Remember that always when you see the ParaView directory, means that you have a state there and you can reproduce that. So you go there. This is the directory I want to open everything. And if I press play, see that is very smooth. Okay, we don't have oscillations or anything. And this that you see here, this is mainly related to the mesh. Okay, so look at that, this is a quartz mesh. So you make it finer, and actually to the mesh. So you make it finer, you will get a better agreement. So just to confirm that, go here and go from 2D to 1D and then put there 100. If you run. Okay, so we are there, so we have a problem somewhere. Okay, I need to increase this value. Okay, it reached the maximum number of iterations. Okay, 432, we are here. Let me raise, load state. And as you play, you have smooth behavior and see how it's evolving. Okay, slowly see that our analytical solution. And everything here was due to the tolerances, everything. But now the important thing is that here we have the full Navier-Stokes equations. And boom, it's arrived there, and you need just to go a little bit more. But there, what we can do is just to increase this one. So if I go here 0.7, or let me go 0.9, we are going to go fast and furious. So see that just 11 iterations were there. You monitor your solution, there are no oscillations, and we're ready to go. We're okay. Okay, delete, load state, you have it here, ParaView, okay, and play, and your perfect match, okay. The thing I mentioned here is that, remember that these are problem dependent, as you said, you here clearly have seen the influence. Let me reduce here, so you go there, run there, see that even is that you choose the low tolerance here, you are very close to the final solution. Since that, okay, I always recommend you go for the consistent. So I was saying, go for the consistent. It would let you use larger under relaxation, and it's more accurate, more stable. But as you put it here, no, it would be the simple normal. Okay, so here you cannot use this very large ORF, but also it would work. But the best formulation is the consistent. Okay, so in this case there is not much different, but when you have a complete problem with turbulence models and everything, you will see the difference. Okay, so also remember that you can go in a selective way like this. So seeing that now in this case here we're putting everything 0.9. Here we're going a selective way. You can relax fields, equations, and you need to know all the equations that you have. So you can put it like this. Okay, so you have some comments there. Okay, how you can do it. So as you see, pretty much as the previous one, the difference that we have now, the complete physics. And now let's move to the next case that will be working the same problem with using PimpleFOAM. Okay, so let me just see here a little bit. Okay, so saving this one here. Okay, again, as you put here over relax, it will diverge. Okay, or it will converge to the wrong solution, but actually diverge. So see here, it diverge. 0.1. Commented 0.1, 1. Okay. And Control D, everything enable, and the mesh. Let's go back. Okay, so I see that also there is no problem working 2D. Okay, you add it like this way, and if you want to go 3D, you can do it with no problem. Okay, so close here. Let me go and let's go to PimpleFOAM. So the setup is pretty much the same, but now we go and we have the time. Okay, so remember that here now we control everything using the time step, but also you have the option to add under-relaxation to stabilize everything. So let's open Control D. So again, you add the scalar transport in the same way, and the sorter is the skin, is the solution. So as you go into and Control D, see that here you have your time step, how you control, but also you can control, in this case, as we are using the solver, you can control, we can impose the maximum current. So what is happening here, and this is important, as mentioned with some TBDs that have the problem at the beginning that they can become oscillatory very fast, that use a low delta T at the beginning, and then the solver will increase very slow the delta T to match this current number. So as you put here a large delta T, is likely that it will diverge. So usually I proceed in this way, small time step at the beginning, and then it will increase a little bit. So you will stabilize your solution. As we skin, look at that standard numerics, see how now we have the Grant-Nicholson here. Set limited Gauss linear, what I like, we have talked about this one. So in T here now, see that it has the linear, but probably it might be better to use, okay, no, actually now it's declared there, but it's using the last one, linear win, this one. Okay. And limited one. SV solutions. So see that what we have here, okay, you choose your methods for all the variables. We're solving here the T, that is the transported variable, momentum predictor to improve the solution. So these are those iterations that you have in your loop. So let me go back here and probably think here, you see that this is how your loop works in the Pimple. So see that this is a momentum predictor. So if you disable that, you are disabled this correction to get better approximation to when you enter to solve this equation. So it's up to you. It's always a good idea to use it, in case the cost that you're going to pay for that is not very high. So usually when you have strong convections, you have really low Reynolds number, you put no there, but most of the problem, you know, that things are moving fast. So consistent formulation, see that also that sometimes you can have high speed flow, so you have a transonic correction there. And see here that this is the Pimple loop, and see that you can add the non-orthogonal correctors, the standard one that we have talked, also the end correctors, we have seen this one, but now you have this new corrector. Okay, so this is what is called the iterative piezo. They call it Pimple. I prefer to call it iterative piezo. Is this loop. So if you use the piezo solver, the normal that in OpenFOAM is called PiezoFOAM, what you are doing is this one. Okay, so you are going like this, and if you use PiezoFOAM, it's recommended to have a low CFL number. Okay. So usually your CFL should be less than 4, let's say, for good accuracy. But when you move into the iterative piece, you see that now you're adding this simple loop. And in this simple loop is where you can add the under-relaxation to stabilize your solution. So you can do sub-cycling, let's call it, or sub-iterations. And these are those iterations. So see that you have initial corrections, and then you are going to improve every single of this correction by using the outer corrector. Okay, which is this one. So see that this is how I like to proceed when I work on Unsteady. So usually I put this to 20, okay? and then you let it run. Okay, you put your tolerances here, you define the variables, so U and P. When they reach these tolerances, the loop will stop and it will move to the next time step. So not necessarily will reach 20 iterations. So let's see what happened in this case, and then also see that you have the option to use under-relaxation. You can go put in everything, or you can put it in the selective way. It's up to you. So here it should be T, where the transported quantity is T. Okay, so let's run this one. And as usual, you have the script, you go there and see that it's running. See that it is here, it's taking all the iterations. So this tolerance that you have here within the loop, you haven't reached that tolerance, so it's taking all those iterations to converge. But see that we have a very good agreement, okay? But probably as you go and measure the time, you will see that this is more time consuming than the steady, okay? So if we reduce, let me reduce the tolerance here. So let me put these values and let me see, just so you can see the effect. So in this case, again, it's taking everything. Let me put 0.1. So this is a particular case. Usually when you go full Navier-Stokes, not traditional case, these two values are good to put for those tolerances. And see here the effect, see that is working, and after 6 iterations is reaching these tolerances of the relative or the absolute that you will see here, the initial residuals, and it will stop the loop and move to the next step. Okay, so it's a good practice to choose and see that it's doing more iterations, it's doing more, okay? But have in mind that this is a particular case, okay? So it's not representative how it works. So it's a good choice to have these values to have the number of iterations, something about 5 to 8, not more than 10. Okay, 10 is too much because you see that you are iterating again, so it will become expensive. So most of the time, in my personal experience, when you use this like this, it takes 5 or 3 iterations, okay? And again, so remember that this will have an strong influence. So if I go here, and if I put here 0.1, I will add more stability to my solution, but I might not reach that final state. And see here that, so now by putting a too low under relaxation, you are losing your time accuracy. The problem is working. You have 1 of a healthy stability. Okay, we know that increasing the under relaxation will improve your stability, but you are losing time accuracy. So see here that what is happening. Everything's super smooth, super stable, but you are losing all your the time accuracy. Okay, so you go, let's say 1, the fastest one. Okay, remember that one also in 1 is okay value, is a good value even in the Unsteady, because here you will have 2 ways to control your solution to make it stable. The most important one is the time step. Okay, small time step means good accuracy, stable solution, and then is this one. So even if you put this one large, you will have the time step is the one that it will improve everything. Okay, but usually my advice is to use the same values that you have as the industry standard, or if you want to use those values, just use, instead of 1, something large, 0.9 or 0.7 it is my default value most of the time. Okay, this is okay. So let me paraphone, delete, load state, go here, part of it, and see that we have a perfect match. Okay, this jump that you see there, that is related, remember, we already saw that one, but that is related to the mesh, so as you make it finer. So that is how you are extrapolating that Newman condition. Okay, so I think we address everything here that we have to address in this case. Okay, let me go back here. So those cases, these cases, you see, very simple cases, but there are there is many stuff happening there. So we'll need to go to complicated cases to understand or to put everything in practice. So play around to this one. With these cases, draw your own conclusions, but I already mentioned. Okay, so let me recap that one. When it comes to SV schemes, for me, this is a standard case and the standard setup. Okay, in this case, it will be for unsteady problems. Probably at the beginning, instead of doing this one, you can start like this, and then at one point just change to this to get extra accuracy. But even the older method is good if you have a CFL number, let's say less than maybe 2, less than 4. Okay, so see that you have it reported here, your CFL 0.4. So here you can go for the Euler with no problem. And also try to increase your CFL number here, and you know how to stabilize the solution on the relaxation and everything. So then for gradient scheme, we have applied limiters. Linear win is okay, unless you really require to use a TVD. Then according to the quality of the mesh, you will set out that one, but this most of the cases is okay. Then SV solution. Momentum predictor is recommended. Okay, consistence also is recommended. This is my standard setup. Again, I like to do at least one non-orthogonal. You need, this is compulsory, you need to do at least one in correctors, and here you put this one to 1, you will default to the standard piso. Okay, so I like to put it like this, and then you add your tolerances. Monitor while it's running that it's not taking too many iterations, not because it's bad, it's because it might slow down your computation a lot. So many people is interested in getting fast outcomes, and this will have a strong influence in that. Okay, but as the solution keep going on, this might accelerate and might go to 5, 4, or ideally 2 iterations. Okay, so and then also play around with your relaxation, but use the industry standards, or probably 0.7 for everything is a good choice when using Unsteady. For Steady, we already saw that. So that's all. Thank you for your attention, and see you next tutorial. Bye.